And we're back. Welcome back from the weekend. And we're back. Welcome back from the weekend. I hope your Memorial, Labor Day. And we're back. Welcome back from the weekend. Today, we will continue on with our discussion and finishing up the introductory material related to Chapter 1. Before we begin, let's go over a few administrative bits. The reading should have been done by now. If you are not, what are you waiting for? Please make sure you get caught up with the reading. You should have already been done by the 3rd, which was last week. Okay, so when we last left off, we talked about threads and processes, and we said that a thread represents all of that contextual information that is needed in order to execute an instruction stream. We also, when we left off, we looked at storage management, and in that, we developed the relationship between the logical view of the storage and the physical view of the storage, and we said that the operating system gives you the illusion of a contiguous tape of storage, but underneath the covers, it's laying out sectors of data on the right track and on the right platter, and presents that to you as if it were contiguous tape associated with a file name. We also talked about cache coherency, and we demonstrated that using the data cache in a multiprocessor system, as well as a cache for a video storage and video delivery system. And so in that, we said it's important to keep all of these multiple copies of your data up to date relative to one another if you're going to have those copies in different locations throughout your system. So let's continue on, and let's take a look at kernel data structures. Now, before I begin, I'm going to bring up a topic of pointers, and this will be important because as part of this course, we're going to be tinkering with C, C++, data structures, which will allow us to look at operating system kernel structures, how it's implemented in an actual operating system kernel, as well as a project that you'll be getting later in the semester, threading, as well as file systems. And the reason for using something like C or C++ instead of Java or Python is that C and C++ gives you the appropriate low-level access to the various parts of the machine that you learn about when you're studying operating systems, whereas Java and Python, part of their purpose is to hide that underlying complexity from you. So an important aspect of kernel data structures is pointers. And so there are many tutorials and things like that online, but let me just play this one to give you a high-level overview about what pointers are doing. In fact, in Java, a reference is Java's version of looking at some object somewhere in memory. Okay.
I'm going to talk a little bit about pointers, if you're not 100% familiar with them. Imagine that the memory we have at our disposal has a series of lockers. Each locker has a number that identifies it. And whenever we create a new variable, something is stored inside a locker. Some lockers are bigger than others, because some variables are larger than others. When we create a pointer variable, instead of storing the actual value we have inside the locker, for example, 6 in this case, we are storing the number of the locker that the value is stored in. So whenever we pass a pointer around to a function, like we're going to do in this case, we are passing some information that the function can use to use the specific locker we are storing in our window class and read it or even change it. Another important point, even though the variable is huge, its address, which means that its identified number, will always be of the same size, which is 32 bits when you're compiling for a 32-bit platform and 64 bits when you're compiling for the 64-bit platform. So when we created the window class, we got a locker, and it fills that with information, which is now whenever we're going to pass a pointer to the register class, we're going to pass the number of the locker or the address of the variable. That's it. So let's do this.
Okay, and so certainly the materials that I'll be assigning will be materials that you'll be reading on for C and C++, as well as constructs in C and C++. All right, so let's take a look at kernel data structures. We talked about a process and thread as being contextual information, all the information needed to represent a program that's executing. For a process, it includes all of the system resources, a representation of them, as well as memory resources, in addition to those parts of the CPU that represents the execution of an instruction stream. And so we talked about threads as being that collection of information, state information on the CPU, representing what is needed for the execution of an instruction stream. And so when we have multiple processes on a machine or multiple threads, these things are often presented in lists. And so this is certainly a repeat of things that you have had in data structures and algorithms too, which is a prerequisite for the course. But I'm just going to go over it at a high level, and in another sitting we'll look at how you do this in C and C++. And so we have a singular linked list, and a singly linked list contains as a list a head element, which is the first element in the list, and a tail element, which is the last element in the list. Now, of course, each list node depicted here has some information, some data. And so we see in this first cell, let me select my pen. So we see in this first cell, we see our data, and I'm going to select the pen color of blue today. So we see in each cell, we see our data, and sometimes if you look in the literature, that's called your payload. Payload, and that's just the data corresponding to each element in the list. Now, in addition to your payload, you're going to have some sort of reference, and that reference in C and C++, well, C++ does have references, but we're going to use the name pointer. And a pointer is nothing more, as the video before said, it's a number that represents the location of some piece of information in memory. And so everything that is stored in main memory, and random access memory, if you want to call it that, sits at some address. And that address is a number representing where in memory that particular byte or word is stored. And so what this pointer is a type in C and C++, and this pointer stores, it's nothing more than a variable, a location. It stores a number, and that number specifically is a location of some other piece of data in memory. And so this pointer then, if it contains the location in memory of the next node or record in your list, well, that's called a pointer too. It allows you programmatically to access the location or the information that's at that next location in memory. And so here we have a pointer field in our node, and that's what you use to access the so-called next node in your list. So we have our nodes. It has payload data, and it has a next pointer, and that allows you to access this next thing in the list. At that next thing in the list, you have your data, and then you also have a next pointer. And then you do it again and again and again. You end up with a list of items until you get to the so-called tail of the list. And that tail is yet another node. It has data, but its next pointer is null, meaning that there's nothing following it. It is the end of the list. And so this is our singularly linked list. We also have another type of list that's called the doubly linked list. And it's called a doubly linked list because if you look at the singly linked list, these are so-called forward pointers. They go from some node at position I to another node at position I plus 1, meaning it's the next node in the list. Now, in the doubly linked list, it's called doubly when it's linked because not only does it have the so-called forward pointer, there's a forward or next pointer, it also has this other type of pointer, this backwards pointer. So it's called a backwards pointer. Now, in the literature, sometimes you'll see the forward pointer called next pointer, and you'll see the backwards pointer called the previous pointer. So we have our payload in our double linked list, our data. We have our previous pointer, and we have our next pointer. So a double linked list is a list, so you're also going to have a head, which is the first element of the list, and you're also going to have a tail, which is the last element of the list. Now, to be the head, what what does that mean? If you're first, that means nobody's previous to you. So in order to be the head element in a list, your previous pointer must be null, meaning that there is no element that comes before you. That's what it means to be the head of a list. And your next pointer, it can be null if there's nothing else in the list, or it can be non-null. It can exist to some value, right? Have some value in that next pointer if there's something in the list following that element. So we have our previous, we have our next, and this is defined as the head pointer, node, head of the list, if your previous pointer is null. So again, these pointers are references to locations in memory, and you use them to access what either the previous node is for a list node or list element, and what is the next node. So here, if we traverse the next, we access the memory location where the second node is stored. Well, here's our second node, there's our data, here's our previous pointer, and here's our next. So just write in previous, and here's next. Now you notice here, the scheme is always data followed by previous pointer followed by next pointer. Now here we have our second node in the list, and because it's second, we know that the head was first, and it is followed by the second. So that means the previous pointer for our second node in the list is going to be non-null, so it's going to be an actual address, memory address, and it's going to refer back to that piece of memory corresponding to the first node. And so this backwards pointer is what our previous pointer value is, and so we can refer back to the element before that node in the list. So here's node 2, here's node 1. So node 2's previous pointer refers back to the head element in the list, and node 2's next pointer points to the third node, node 3 in the list. So we can traverse the list from beginning, from head to tail, by following the next pointer. So we say, oh, go to the next address, go to the next, go to the next, and so forth. Likewise, if we're at an arbitrary node in the list, we can traverse back towards the head by using the previous pointers. So here's previous, here's next. For node 3, we traverse the previous pointer, and we traverse the previous pointer again, and that gives us back the head. So we can always get to the head node if we keep traversing previous pointers until that previous pointer is null, and we know we're at the head element. So we can move in the direction from tail, in the direction towards head, or from head in the direction towards tail. To do the former, to traverse the list from tail to head, we traverse the previous pointers until we get a null. And to go from head to tail, we traverse the next pointers until we get a next pointer of null. Because recall from before, the tail element has nothing following it, and therefore its next pointer is going to be null. Likewise, we also have this circular linked list, and it's called circular because the tail element leads you back to the head element. So imagine if this were the head element here, the first item in our list, and we also have the tail element, the last one. Now, we just like the singly linked list with one exception. So we have our next pointer. So here's our record, our data. Here's our next. And each node has a next pointer as well, next. But on the tail element from before, when we talked about the singly linked list, we said the tail element is defined as having a null pointer, a next pointer that's null, right? Because nothing follows it. In a circularly linked list, our tail element's next pointer, instead of being null, it's going to refer back to the head element. So if you want to traverse from some item in the list getting back to the start, well, you circle back, as it were, to the head element. And so the circularly linked list can be important for certain things called a ring buffer. If you are consuming resources, and when a resource is old, you want to reuse it, but you don't want to pay the cost of always going back to the head, you can continue to cycle back, if you will. Okay, so these are some standard data structures, and these types of data structures, these different types of lists, are all over the place in operating systems. Okay, we also have a binary tree, and this binary tree is called binary because if we have a node, as you covered in data structures, a node has two children, a left child. So in this example, here's the left child of this top node, also our root node. And we also, each node has a right child. Okay, so a binary tree is called binary because every node, including the root and or the leaves, these are the leaves, have at most 2 children. You can either have 0 children, well, that makes you, here the leaves have 0 children. You can have 1 child, or you can have 2 children. Now, there's a particular type of tree called the binary search tree, and for this binary search tree, the organization is such that each one of these nodes holds data, and the data for the left child is always less than equal to the data for the right child. Now, when you make this arrangement for your binary search tree, you get a lot of nice properties. It speeds up your search tremendously if you're trying to search for some value. And so with this binary search tree, your search performance is in big O notation, which you've covered in the algorithms and data structures 1 and 2. Big O of n, because you have n many nodes. But if you arrange the binary tree such that it's so-called balanced, and what balanced means, to jar your memory, is that if you were to examine the number of nodes on the left-hand side of the tree versus the right-hand side of the tree, it tends to have equal amounts, or tries to have equal amounts. When you have this property and you try to perform your search, well, you get a nice speed up. You get a logarithmic speed up. So instead of taking big O of n, it takes log n, which is a great speed up, especially as n grows very, very large. Okay. So let's take a look at this search, and I've included a link down below that talks about different types of traversal algorithms. And with the same data structure, and that's another beauty why binary search trees are so popular and they're so powerful, is that with the same data structure, the same arrangement of data, right? So you'd imagine here each node has data, and it has a pointer called left, a left pointer, and a right pointer, right? And so you could imagine now left pointer is going to point to memory or refer to memory. That's going to be your left child, and this one's going to be your right child. So likewise, now we have data, and we have a left pointer, and we have a right pointer. Likewise, we have data here for the right child. There's a left pointer and a right pointer. So when we talked about having no children, 1 child, or 2 children, that corresponds to whether the left and right pointer actually contain values or if they contain null. Okay? All right. So the beauty of this is for the same data structure, here's my tree data structure, my binary tree or B tree, and you can get different types of searches just by the algorithm you use to visit or the data in each node. And so the difference in these different types of searches, so-called in-order search, pre-order search, or post-order search, corresponds to when you visit a node. And visiting a node corresponds to when you actually read out the data value of interest. And so for in-order search, well, what do? Well, the scheme is you visit the left child, you traverse left child, you visit a node, the node, and then you traverse right child. So let's take a look at this. So you start out at the root of the tree, you visit the left child, okay, and then you're going to see, all right, well, I'm at a node here, I traverse the left child. If you run out of left child, you don't have any, that's when you visit the node, and then you traverse the right child. So we visit the left child, traverse the left child, okay. Do we then traverse the left child? Okay. We don't have any left child that we traverse, okay, so this one has a null for the left child, A does. So we visit the node, we get A, and then we traverse the right child. We don't have a right child. So now we come back up. We're done traversing the left child, and now we visit the node here. And so what determines whether it's in order, pre-order, post-order is when this visit the node happens. So you notice here the first thing I did for the in order, traverse the left child. And then the second thing I did is traverse the right child, visit the node, I mean. And then the third thing I did was traverse the right child. So the visiting of the node is in order from left to parent to right order. So if we keep this schema up, we get with an ordering of this particular binary tree that is alphabetically ordered, A, B, C, D, E, F, G, H, I. And I'll leave it to you to go through this example yourself. With the pre-order, what happens is you visit, in step one, visit a node for the particular node of interest. The second thing you do is traverse left child. And then third thing is you traverse the right child. Okay, so visit a node, meaning to examine the data. Okay, so here we're at root node F. First thing we're going to do is visit the node, okay. Then we're going to traverse the left child, then traverse the right child. So we traverse the left child, and then we come to another node. So the first thing we do for each node is we visit the node. So we visit the B, and then we're going to traverse the left child and traverse the right child. And so we start out, and then we go to A, and then we're going to visit the node. We write out A, and then we're going to traverse the left child. There is none. Traverse the right child. So we come back up here, and we finish that we've traversed the left coming from B. We traverse the right child, and we visit D. So we end up writing out the characters, the data in each node, in the order that we visit, and the visit order comes first. So we say F, B, A, D, C, E, back up here, G, I, H. F, B, A, D, C, E, G, I, H. Okay. And then lastly, we have what's called post order. And in post order, it's called post order because the first step you take is you visit the left, or rather traverse the left. You traverse the right. And then the last thing you do is visit a node, the node. And that's for each node. Okay, so we start out with F. We traverse the left, okay. And then here, that's a node. And for this node, we traverse the left, and then we're going to traverse the right. Okay, so we'll traverse the left. All right. And then here, A, we traverse the left. All right, there is no left. All right, we traverse the right. There is no right. So then we visit the node, and we write A. Okay, so we come back up here. All right, we finish traversing left. We traverse the right. That's D. Then here, we traverse the left. Okay, C. We traverse the left. There is none. Traverse the right, and then visit the node C. So that's C. So it's A, C. We come back up. We traverse the right, left, E. So A, C, E, D, and then B. So A, C, E, D, B, H, I, G, I. And so here we get a different ordering. This first ordering is so-called in order. The second ordering is called pre-order. You visit the node first, and this third ordering is called post-order, or for each node you visit that node's data last, after traversing the left child and the right child. Okay, and so I have a link here, and I'll leave it to you to look at the material on that link, and there are many other sources available on the internet to remind yourself about in-order, pre-order, and post-order traversal for a binary tree structure. Okay, so we also have another data structure called a hash. And a hash map or hash table is a function that speeds up a potentially large search based on this thing called the hash function. And so a hash function takes some input called a key. It could be a string, it could be an object, and it returns back a number, and that number is an index into a so-called hash table. And so as a result of computing your hash function, there are many such hash functions you can compute, you get a string of binary digits, and this represents the status of n items. Literally, it's used to calculate an index that you're going to use to index into a table or an array called your hash map. And at each location in this hash map is going to be stored a reference or pointer to some value. And so a lot of these data structures are defined in the Linux kernel header files. And in fact, through this semester, we will examine some of them. And so I encourage you, please do watch the YouTube video. A URL is listed below. It's a great description of what a hash table is and a little bit about what a hash function is. And so here, the key is with a hash function, it tries to distribute as evenly as possible across these so-called slots. There are n many slots, or in this case, n plus 1, because it starts at 0 in this figure. But it tries to distribute the load of various types of keys or values associated with your values. And so if you distribute this load across, the access is going to be approximately 1 over n plus 1, the size for each hash slot. And so if two keys hash to the same slot, you start a linked list at each slot, and that's the so-called collision. And so how you resolve these collisions in the hash function, one is called chaining and one is called direct addressing. You can rehash, or you can just add them on a linked list in each slot, and it gives you a much faster access time instead of traversing through a singly linked list, doubly linked list, or circular linked list. Okay, so let's go on to computing environments and talk a little bit about open source as well. And so computing environments in traditional case, your desktop was a standalone general purpose machine. And it sort of got a little bit blurry as systems became interconnected with one another, i.e. the advent of the internet and networking in general. And so one type of system called Portal gave access to internal systems. So our content management system for the division, which is, I guess, now, I don't know where the development of it is. It is a type of portal. Now, portal, it was thought that, okay, well, there are lots of things internally within an organization that people frequently might want to do, like add drop forms at DSU or student employment. And so they can use web-based tools and effectively stand up a website or set of websites that are not accessible to the outside world. They're only accessible to people within an organization like DSU Campus Network. And it's a great way to organize useful information that you need for the operation of your institution or your organization. And so Portal provides web access for internal use only, because there are certain things you don't want anyone across the internet to be able to access as it pertains to DSU operations. So we also have network computers, and these in the beginning were called so-called thin clients, and they're basically terminals that didn't do very much except for act as your input-output, your keyboard mouse input, as well as your visual output on your monitor and maybe some sound, but all of the work was done on a more powerful computer, be that web-based or non-web-based. And then mobile computers, which you're all very used to now, your handhelds like your smartphones and your tablets, these interconnect via wireless networks, and the model is to run mostly graphical interface type stuff on the mobile device, and all of the real heavy-duty computation happens on a powerful server, and the mobile device connects back to the server in order to run the application. And so networking became very ubiquitous, and even in the home, networking is very ubiquitous, so much so that people in the home, it's very normal for a home computer to have firewalls and certain other protections in place to try to protect that information on your home computer, like your photo library, your taxes, and things like that, from internet attacks. Okay, so handhelds and smartphones and tablets are very different than traditional laptops. They usually have a lot of sensors now, and have lots more features that involve things like GPS and gyroscope, all sorts of lots of tools that allow you to do things like location-based applications like maps and other things like that. And so cell phones use Wi-Fi as well as cellular data networks, and they will often switch seamlessly between the two if your cell phone senses that it is in good connectivity range with a wireless Wi-Fi network. It'll use that for data. Otherwise, it will connect to the cell phone network and use the cell phone data. The leaders in handheld smartphones are Apple, and their iOS is the operating system, and Google Android. Android is Linux-based underneath the covers. We also have distributed computing environments, and distributed computing consists of a set of separate, possibly heterogeneous, so different systems that are networked together. Some might have fast I/O, some might have more computation, some might have special devices, maybe things that compute time accurately, maybe a lot of GPU for doing matrix vector operations. And so they're networked together. And the network is nothing more than a communications path, and the predominant protocol is TCP/IP, Transmission Control Protocol, Internet Protocol. If you want to know the details of that next semester, please take computer networking, and you go through that in all of its detail. So the most common types of networks are the so-called local area networks, so within a particular work group, as it were, wide area networks across work groups, and a LAN will be something like a whole department at a university, and a wide area network would consist of interconnects between, say, computer information sciences and arts. So you have each department is a local work group networked together, and the wide area stitches together all of those local work groups into a so-called wide area network. Then there's also a metropolitan area network, which deals with connectivity on a city and surrounding suburban scale. And there's something that can go very small, something called a personal area network. Bluetooth is a protocol and a technology for personal area networking, where you're going only merely a few feet trying to pass data between devices. And so when you have, say, a Bluetooth headset, you don't want your Bluetooth headset to broadcast data across the country someplace to maybe Silicon Valley. You're just really communicating between your headset and your phone, which are usually no more than 2 or 6 feet away. So these distributed computing environments have so-called network operating systems, and they're operating systems, just like we've been talking about, but it also provides features that allow you to do things across systems connected by a network. And this generally means communication schemes. And these communication schemes allow processes on these different computers, whether it's over local, personal, wide, or metropolitan area, to exchange messages. And they can exchange messages in a way that gives you the illusion that you're operating on a single system. So when you call a function, there are facilities in distributed systems that take that function and send data across the network, call that function on another machine, get the result, and pass it back across the network. But to you, it looks like your function call executed locally. That's called remote procedure calling. And so distributed computing extends beyond operating systems with these facilities to give you this illusion of a single system by adding facilities that more easily allow a number of processes to interact with one another to give you the illusion that it's a single system that you're using. And so one type of computing environment that you're probably very familiar with is so-called client-server computing. Now, of course, in the early days, it was so-called dumb terminals. And they're called dumb terminals because they had very little functionality, and their whole purpose was to take your keyboard and mouse input, send it to the computer, and take the result and display it on a terminal. And so these dumb terminals, very lightweight, so-called thin clients as they were called a little bit later, were supplanted by smart PCs. Smart meaning that they have more computation. There's a lot more happening on the PC. It wasn't just relaying the inputs and displaying to you the results. And so many systems now are servers. And oftentimes these servers are just sitting out there, and your machine, your application, is just a series of requests, i.e. client requests, to these servers that are sitting there in the background waiting for incoming requests, perform work corresponding to the request, and then return back the result. And so a compute service system provides interfaces that allows your client to request services, to send requests. And one request might be, say, on an e-commerce site, look up this item, and that item will have a level of inventory in the database and maybe the cost and other information like that. And so we also have other types of service systems, things called file server systems. They have interfaces that allow clients to read or store information. And so Dropbox is a perfect example of a file server system, or iCloud is a perfect example as a file server system. And so on your machine, when you say save this to iCloud, let's say you're saving a document to iCloud or saving a photo, what you're really doing is saying file save, and you're sending that command to the file server system. And that iCloud file server system is storing that file in the cloud, so to speak, but it's really sending that information as if it were a local file write, and that file write underneath the covers in this distributed system is sending that data across the network, that file information for your picture file, to the server for Apple's iCloud data center, and that's writing it to its local disk, send back the response that says, yep, I've written it out, and you're done. And so here we have the server, we have our network, and then we have a number of client machines, a desktop or maybe a laptop or smartphone, and you send information through the network to the server. It computes something and sends back the response. And so if you've ever used something like Siri or Amazon Alexa, right, your desktop device would be Amazon Alexa device, and you speak to this Alexa, so there's you, right, and then you say something. Alexa takes that voice signal, encodes it into data, sends it to the server through the network, and maybe that is encoding what time is it, and it looks up on its clock to see what time it is. Here's the clock, and it says, oh, it makes sense that you're saying what time is it. It goes, accesses the clock, sends back to the response, and then the speaker plays it. It's 2 p.m. And so for you, you get the sense that, Amazon Alexa is doing all this work, but it's not really Amazon Alexa. Amazon Alexa is just a basic sensor that knows how to send voice signals across the internet, or digital representations of voice signals over the internet. We also have so-called peer-to-peer systems, and a peer-to-peer is another type of distributed system. Now, with a peer-to-peer, you don't really have dedicated clients and dedicated servers per se. With peer-to-peer system, each device, and here's a device node, it acts like a client, and it also acts like a server. As a server, it can receive commands and send back out responses. As a client, it can initiate commands. And so with this peer, the nice thing is that peer-to-peer systems bring a property called self-scalability. And their popular peer-to-peer systems include things like Nutella, Napster, and BitTorrent. BitTorrent is a very important one. And so what does this self-scalability mean? It means that as you add more nodes to the network, you also increase the capability. So how might that work with something like BitTorrent? Well, with BitTorrent, what are you doing? Each machine stores a file, parts of a file, and when someone new joins the network, they might want that file, and instead of loading it from one machine, they're loading parts of it from multiple machines. And so if you're loading parts of a file from multiple machines, you end up getting that data much, much faster. And so each node that joins the network that can communicate with one another, and they must register their presence so that everyone knows that they exist, everyone else on the network. And they also look up information, say who has this file. And so oftentimes you have what's called broadcast requests for service, because you don't know in the beginning who's there, so you have to kind of shout so that across the network so that everyone can hear you. And that's a so-called discovery protocol. Examples like BitTorrent are really, really popular for file distribution, very rapid file distribution. And the reason why you get this higher bandwidth, so to speak, or the illusion of higher bandwidth, is because you are in aggregate downloading pieces of files from multiple locations. And so BitTorrent is a big example of a peer-to-peer system. All right. So virtualization. With virtualization, it allows an operating system to run applications within other operating systems. And this is very, very popular because these days you don't just run on one platform. So if you're running on Windows, you might want to run Linux application. If running Linux, you might want to run a Windows application. If you're on Mac OS, maybe you want to use an application that's only native to Microsoft Windows. And so there are different ways to enable this. One is called emulation. And with emulation, there's a direct simulation of the underlying CPU. So emulation is used when you have a source CPU that's different from a target type. So imagine you're running on Intel processor, and maybe you want to run something on ARM processor, advanced RISC machines. So what you do, you have some software that simulates, it's just a program, and that process or program simulates ARM architecture, and it allows you to run these other applications written for another computer chip on a different one. And so this is very slow, and it's often used in various cases when you want to test things, or maybe you want to support some legacy application. Now, in computer languages, a type of emulation happens, and this is called interpretation, and this is what Python does. Essentially, when you have a computer language and it's not translated to the binary code for that particular processor, you have this thing called interpreter runtime. And what this interpreter does, it reads the text of your program, and then it decomposes the commands in your program, and it executes them one statement at a time. And this is exactly what a Python interpreter does. So when you run the command Python, what you're doing is running the Python interpreter, and then you follow it with the name of the Python file that you want it to run. Okay, so we also have another type of virtualization. This is virtual machines, and this is a very old concept that was pioneered in the 1970s by IBM. Now, virtualization, the idea is that you have somewhere sitting in your system, your operating system, a mimicry or an emulation of a target platform. So it's almost like on a machine, you have a program running, and that program simulates all of the parts of the computer. It simulates the processor, simulates the memory, simulates the disk, and so forth. Now, as a simulated machine, what can you do on a machine? You can run operating system. So what you do with this program, this virtual machine, is nothing more than a special type of program. You run this process, and that process simulates all the parts of a machine. So that means you can, in a virtual way, run multiple copies of an actual computer. And on each one of these computers, you can install an operating system. Now, the operating system you install on it, it doesn't know that it's running on a simulated piece of hardware. It thinks it's running on an actual hardware. And so with virtualization, you have a so-called host operating system. The host operating system is the one that runs that VM machine, that simulated platform. And the guest machine is that instance of the simulated computer, and you install the operating system on that. So that's called a guest operating system. So suppose I have a Mac. I'm running Mac OS. I install Parallels, which is the virtual machine manager, a popular one, VirtualBox as well as another. So I run Parallels or VirtualBox. I tell VirtualBox or Parallels to create an instance of Intel hardware. It does that, and now I install Microsoft Windows on that simulated virtual hardware, and that Microsoft Windows is the so-called guest operating system. And so this allows us to run operating system instances on another machine, and it is very useful if you're testing. Maybe you're testing virus defenses, and you don't want to damage your actual machine. You run it on the virtual machine instance on the guest OS. Now, it's not only set aside for running, say, Microsoft Windows on Mac OS. You could also, on a Windows platform, run multiple virtual machines that each run Windows. Or you could have multiple Microsoft Windows machines running on Linux. So it could be multiple Linuxes running on Linuxes, Windows running on Linux, or Windows running on Windows or Linux running on Windows. Now, Mac OS is a little bit different because Apple does not make it easy for you to install and run Mac OS on anything outside of Apple hardware. And so the Virtual Machine Manager provides all these services, the ability to simulate your entire hardware. So imagine if you had an instance of a von Neumann architecture with CPU, with I/O controllers, with main memory, all that stuff, with the bus, and instead of being actual hardware, it's really just a program that is simulating or implementing this hardware. And so there are cases where you want to run multiple OSs, and I alluded to that before. Virtualization is really, really popular. And in fact, Amazon Cloud Services presents virtual machine instances so that you can run multiple platforms that you can access across the internet, but you pay for that time. And so a virtual machine manager can either run as a process, but there are some cases where you want them to be very, very fast, and they can run natively on the hardware. So in that case, there is no operating system. A virtual machine manager literally runs on the hardware itself, and when you boot your hardware, you immediately select a guest OS which you want to run. And so there are lots of vendors for virtual machine managers, but it's mostly the big companies like VMware and Citrix that do this. And so here in this frame, we have on frame A on the left, we have our processes running in memory. You have the operating system kernel that share the underlying hardware, right? That's the single machine instances. In the virtual machine manager case, the so-called hypervisor, and let me write that out so that when you see it in the literature, you know what it does. It's called a hypervisor. You have your hardware down below, and then you have your virtual machine manager, your hypervisor, running right on the raw hardware. So now this virtual machine manager, it knows how to create a simulation of the underlying hardware resources. In this case, 3 of them. We've done that. Virtual machine 1, virtual machine virt 2, virtual machine 3, and then you install your operating system on top of that simulated low-level instance of the machine. So maybe that's going to be Linux. Maybe this one is going to be Windows you install, and maybe this is going to be another version of Linux. Maybe it's Ubuntu Linux, and maybe this is Kali Linux, for example. So then, once you install those operating systems, Kali, Windows, and Ubuntu Linux, you install whatever applications run natively on Linux as well as on Windows. And these processes don't know that they're not running directly on an operating system that's overlying hardware. They believe that they're running on these hardware instances, right? And these hardware instances just happen to be a simulation produced by the VMM, the Virtual Machine Manager. Okay. And so this is a hypervisor running on the so-called bare metal on the actual hardware. So distributed computing environments deliver computing, storage, and even applications as services across the network. And this is immensely popular, and this is where computing has been going for the last maybe 15 years or so. And so this distributed computing is a logical extension of virtualization because it can virtualize just about anything that you need to stand up a pretty substantial organization. Now, Amazon has made a fortune off of their elastic cloud, Amazon EC2. It has thousands upon thousands of servers, millions of virtual machines, lots and lots of storage across the internet, and you pay based on the usage. So it's almost like the electric company or the gas company, right? You pay based on your usage for the service. In the case of something like Amazon Cloud Services, Microsoft Cloud Services, or Google Cloud Services, you're paying for computation. And with all these advances in distributed systems, now you can deliver all sorts of things, applications, infrastructure, databases, all kinds of stuff. There are all sorts of cloud service types, computing environments. There's public clouds that are available to anyone. You just have to pay for it, like a utility. There's a private cloud run by a company for their own usage. You also have things that are hybrid, mixture of public and private usage. And so there's all sorts of services you can deliver. Software as a service, that's kind of like an application. So when you go to Google Docs or Google Applications, you bring up your browser, you connect to it, and now all of a sudden you can use a spreadsheet or word processor right in your browser. There's also something called a platform as a service. Platform as a service is a software stack that's tuned for certain types of applications. So suppose if you want to have a database-backed web service for shopping site or commerce, well, platform as a service is a set of APIs that you call remotely on a server, and it has a set of software components, everything that you need, like database, like processing of e-commerce transactions, the ability to draw pictures of things in a catalog. It has everything you need, a collection of services, service APIs, everything you need for certain types of applications. This is called platform as a service. You also have infrastructure as a service. Now, infrastructure as a service gives you things that you need in order to create applications. And so things like storage, things like the ability to back up, things like Carbonite, the ability to back up your software, all those infrastructure pieces you need for an enterprise. And so with all of these, you can literally outsource by pay per use the amount of computing infrastructure. So you might be asking, well, why would I want to do this? Well, what happens when you have your own infrastructure? You buy a bunch of computers, you have to install the operating system, you have to keep the patches up to date, and then, every few years you have to upgrade your hardware, you have to hire somebody to manage this infrastructure, you have to put it in a room somewhere and pay to keep it cool with a ventilation system. Maybe you buy a building, maybe you rent a building, you have to heat and cool the building. That's a lot of money and that's a lot of work. Whereas with these cloud computing environments, well, you outsource it to someone else. Instead of having to have that constant set of costs and time that you have to devote to these areas, you can just rent it by the hour, by the minute, and so forth. So in very short order, somebody can focus just on what it is you're trying to do. Maybe you have a nice algorithm for doing mapping. Well, you don't have to sit there and say, let me build a data center. You just rent the computation you need, and you focus just on what your craft is. And so this cloud computing, these different types of services have revolutionized and also the industry, and also been a facility that fosters a lot of interesting creative types of solutions. And it has only accelerated things, and it's only getting better. So in cloud computing, you have lots of different components. You have virtual machine managers. You have other tools to manage all of the resources in the cloud. You have different operating systems, and you also have things like load balancers that spread the load or the amount of work requests coming into the system across various instances so that you don't bog down one or small number of machines. And you also, these things maintain firewalls to make sure only certain types of messages are getting in and certain don't. So if you had a data center on campus, for example, you'd have to manage all that security, whereas if you rent cloud services, the organization that does that very well, they handle all of that. So it allows you to focus on your craft and not on all these ancillary considerations that you have to focus on when you're running a data center or distributed system. And so computing environments also include real-time embedded systems. Now, real-time embedded systems are the most prevalent type of computers around because there are many more devices. If you think about things like your alarm clock, you think about things like your washing machine, you think about things like your electric meter on your home, there are many more devices around than there are computers. And so these devices are very specially purposed. And they're not general, and they often run an operating system intended to give results in a certain time schedule, in a timely fashion. And so more and more, these devices are becoming internet connected. And so it's going to be very interesting what the future cloud-based systems are going to be like, with the assumption that you now add timeliness to the considerations for your algorithms that run. So there are many other specialized environments, and real-time OSs have fixed time horizons. Not only do you have to get an answer, you have to get an answer within a specific amount of time. And the reason for that is that if, say, like autonomous driving, right? If there's a car that's stopped ahead, you have to start braking within a split second. You can't afford to have something take 30 seconds to compute. And so the operation is correct, not only for the value of the output, but also that it was done in the suitable amount of time. Okay. And so there are all sorts of other specialized computing environments, and some operating systems have set up special tasks to address the peculiarities and the intricacies and specifics of those environments in which they operate. Okay. And so-called open source operating systems was a huge revolution. In open source operating systems, the source code is made available, not just the binary. Now, certainly for Windows and Mac OS, you can gain access to parts of the OS if you join the developer networks. But for open source operating systems, it's different from that. For free, no cost, you have full access to all the source code. And if you feel that you can improve the operating system, have at it, modify the source code, recompile it, and start giving away or selling your own version of the operating system. There's nothing stopping you from doing that. And so a lot of proprietary internals or details, companies like Microsoft and Apple consider them as trade secrets. And so they're never going to let you in on that. But these open source operating systems generally have what's called digital rights management. And so this was started a long time ago by the Free Software Foundation. They thought software should be free. You should be freely available to distribute it and to modify it. And so there's certain licenses like the GNU Linux license and the BSD license, and to a lesser degree the MIT license, that allow you to distribute the source code and allow you to modify and effectively create your own variant if you choose, and to be able to distribute that. So if you took source code to Windows and then you decided to make a change to it and then start selling it as your version of Windows, trust me, you would see yourself in court very quickly, and Microsoft would say, stop that. All right, so there are virtual machine managers, like a free version of VMware Player, but there's also VirtualBox, which is completely free, and you can use that to create guest operating system instances, guest machines, and run multiple OSs. And the nice thing that VirtualBox gives you, it's free, but it also runs on all the major platforms. It runs on Linux, it runs on Windows, and it runs on Mac OS. And so these links, I'm not going to read them off. Please visit these links. They will tell you about all sorts of open source Linux distributions, versions of operating systems that are available. This is not exhaustive, but it's a pretty good list of the more well-known open source operating systems. So with that, that's all I had. Please make sure that you have caught up with the reading. You should have been done with the reading pages 3 through 51 on the 3rd of September. If not, please make sure you are staying on top of it. Homework 1 is due this evening. I look forward to your solutions. That is a typo. Homework 1 is not due on the 1st. Homework 2, rather, is due on the 10th, which is today, Tuesday, the 10th of September. No, that's not correct. Homework. Make sure you are getting caught up with the reading. You should have been done with the reading by now. And this third point, that is a typo. Homework 1 is due on the 10th of this month. And I will see you on Thursday.